something that. Okay, I think first of all, so I have to give a very short introduction for the Professor Gerrit Lohmann. So hello everyone. So today is our Future Ocean Forum. So we are very honored to have the talk from Professor Gerrit Lohmann from the AlfredWegener Institute for Polar and MarineResearch in Germany. So I have to take a moment to introduce Gerrit and highlight his remarkable contributions to this field. So actually, Gerrit, they provided me with a very long introduction for you, but it may be too far away for the students. So therefore, I just introduce Gerrit based on what I know. Okay, so Gerrit is a distinguished researcher with expertise in paleoclimate. He has made significant contributions to understanding ocean circulation dynamics and cryosphere interactions. So throughout his career, Gerrit has been working at very famous institutions like MaxPlanck Institute and also the Earth ScienceCenter in Gothenburg, and also now he's the professor for the University of Bremen, and also he has also worked at the University of Hamburg. So in summary, the take-home message is that Gerrit teaches a lot with students and postdocs all over the world. I mean, really, he writes a lot. With publications fulfilled his office, and also his impact is a lot. Brought him to be the elected member of the Academia Europaea for his outstanding research. Then, so we come to the theme today is the lessons from the past, clues from data theory and models, and so let's welcome Gerrit for his very excellent talk.
Thanks a lot for this kind introduction. I also feel honored to be here. The next 30 or 40 minutes or so, I will talk you about lessons from the past. Actually, I was born when the CO2 content in the atmosphere was 320 parts per million. If you see how the evolution is in Earth history over the last 800,000 years, it always fluctuated between 180 and 280 roughly. And this 180 parts per million content in the atmosphere is related to ice ages, whereas 280 we call interglacials because they are between the glacials, they are warm climates. And this information is obtained from ice cores, shown on the right. It's another cruise, but basically you drill pieces of ice and you analyze the bubbles, the content in the air bubbles in the ice, and then you can measure CO2. So I think the most important contribution of paleoclimate is to climate research is this curve, giving us a long-term perspective of carbon dioxide and also oxygen isotopes, which is a measure of temperature. So we are now at 425 or so. So the variation between ice ages and interglacials is now less what we have done as humans in the last century. What is then the consequence, attribution of that? And Klaus Hasselmann at Manabi got the Nobel Prize 2 years ago for that. So basically, if you run a climate model that is shown in red, the reddish curve, with carbon dioxide and the human impact, so carbon dioxide, but also land cover, you get these reddish curves. So it's many reddish curves in the back. So it's uncertainty and internal variability in the system. But the red curve and the black curve are consistent. So observations, the black curve is somehow consistent with model results of fluctuations. Whereas if you don't allow the model, or you switch off the carbon dioxide forcing and you only take the natural drivers like volcanoes and sunspots and internal variability, then you get the green curve and the shaded area. So this is inconsistent with observations. That means that's somehow the proof that humans are active. At least it's very obvious since 50 years or so. But what is the question now in terms of, that's a global mean temperature change from the pre-industrial time, which is at roughly starting at 1850. What is the spatial pattern of that? So basically, what is the pattern on the globe? And it's quite different. And if you look at these different scenarios, so what will be the Earth on a 1.5 degrees warming, or 2 degrees, or 4 degrees warming? It's quite different, but what is common is the warming is stronger over land than over the ocean, and is strongest at the Arctic realm. I will come back to that. That has enormous consequences on the Earth system, that we have the strong warming in the Arctic realm. Okay, and this is a spatial pattern, so it's quite interesting. What is this? What is the pattern in if you see a simulation? This is a simulation what we did at ARVI with our climate model. Here's on the lower right you see the time. Again, you see the strongest warming is in the Arctic or polar latitudes and over land. In order to avoid this fluctuations, we made a 10 years running mean. So this is somehow the output of a climate model. And then you can see what will happen until the end of the century. This impact, I mean, this is due to CO2 emissions from energy use. And you see 3 centers of action. The biggest one is United States, then Europe, and then Asia, China, and Japan. That is the historical emissions. This is emissions from fossil fuel and cement production in the year 2013. So then Asia is even stronger. However, it's also a problem, but to calculate that, because export and import of carbon, if you're living in a nation where it's a strong export, like in China or Germany, you produce something and then you export something. So it's this graph is also difficult. But what you see, how small is Africa and South America, and how the world is different. And the impact is quite dramatic. I mean, you can make an impact on extreme events, but this is an impact on sea level rise. So if you have 5 meter sea level rise, which might happen in a couple of 100 years, then countries which are strongest affected is Netherlands, also in Africa, also in China, India. And what is then the pattern of temperature change in the last 40 years? This work, what we did with Hu Yang in Zhuhai, you see the strongest warming in sea surface temperatures is in the subtropics. It's not in the polar latitudes, it's in the subtropics. And it's interesting that the strongest warming is in the subtropical gyres, where you accumulate heat. And this is quite interesting because this pattern can be obtained in different ways. One way is the satellite observed warming on the left-hand side. The right-hand side is a similar pattern, except in the El Nino region, is if you make an initial shock of a model experiment, so 4 times CO2, and then you see how the system reacts in the first couple of years. And then the initial shock of the climate system is relatively similar to the observed ocean warming. What is the reason for that? There's a very simple reason for this pattern. This is the age of a water mass. So every water mass has an age. When it's close to the atmosphere, it's an age 0. And then the water parcel then sinks down, and if there's no contact to the atmosphere, it's becoming older and older. That means the bluish color means surface water, which is more upwelling from the deeper levels, and the reddish colors are so-called young water, so contact with the atmosphere. It's kind of tracer in the ocean. And this tracer you can also measure with carbon C14 in the water. It has a similar pattern. So whatever tracer you have kind of this pattern. And the reddish color means young water. That means contact to the atmosphere. And this pattern is almost the same as the warming pattern. That means the warming is strongest where you have the strongest where you have downwelling and not upwelling, where the water is young. So basically, the first order effect of our recent temperature warming in the ocean has something to do with the age of the water. It is different if you see in the model simulation, now the lower panels, if you make an equilibrium simulation, that means you simulate a couple of thousand years and then see what is the response. And then the response is strongest at the higher latitudes. It's different than the initial warming as in the early stage of the warming where we are now. And you see also on the lower right, that is the equilibrium ocean warming with the 4 times CO2 world, up to 7 degrees or 10 degrees warming in the ocean, which is enormous. And this has happened also in the past. This is for the mid-Pliocene ocean warming. On the left, the pattern is very similar. The land sea geometry is also similar. There are some changes, but there are minor changes. So you see that that will be also part of my talk, that it's quite useful to study the past in order to understand the future. What is a big challenge, especially in the Arctic? There's a lack of data for this warm climates. So the last big expedition took place in 2004 with 3 ships in the Arctic, and they drilled data, but they were not able to get data from this Miocene climate where the temperature was much higher than today. On the right, you see the temperature distribution of models, the lines, for different CO2 levels for this Miocene climate. And the black dots with arrow bars are observed or reconstructed temperatures. And you see that in the tropics, it fits quite well. So the temperature in the model and the data is okay. But at mid-latitudes in the northern hemisphere, there's a quite mismatch of that. So the data is much warmer than the models. And at polar latitudes, there is no data. So that's part of a bigger project. I received the ESC grant in Europe, where we received in total 14 million or so, where we make an expedition to the Arctic to drill this course, but also making model studies in order to understand what has happened in the past and what will happen in the future with the blue Arctic Ocean. So that is more symbolized here. Imagine a person living in 50 years or so. The satellite pictures would be quite different. At least in summer, we have an ice-free Arctic Ocean, so it will be a blue ocean instead of a white ocean. What is then why we look again to the past? So that's current temperature changes, what we expect in the future. And then we can look into the past for the Miocene, so between 5 and 20 million years ago, Pliocene about 3 million years ago, where we had also Greenland was smaller, much smaller, almost no sea ice, or in the last interglacials, where also the sea ice was much lower, also Greenland was reduced. So this is a challenge that we face, a very warm Arctic and climate system in the future, and we want to understand the system and this impact. There are two ways to understand this in terms of models. And these two ways I follow in my research strategy. One is to go to very high resolution, and in our case, a very efficient climate model where we can simulate even details here in the Arctic Ocean. The sea ice is shown here with cracks and all this complicated stuff. That is one direction of research, going to very high resolution, and I will come to that, why it's necessary. And the other way of direction is including more components in the system. And this is one example, one result of a simulation where we have interactive Greenland ice sheets. And this interactive Greenland ice sheet will, in the climate simulation, will be seen here. You have a couple of 100 meters ice loss at the some coastal sites in Greenland in the future. And this will impact sea level and freshwater balance in the Arctic and the Atlantic Ocean. What is then the impact on marine heat waves? And this will be published with a colleague, a PhD student, Rujan Gu, in January 6th. So in a couple of days, it's published in Nature Climate Change. What we analyzed is high resolution model and data. So heat waves means you have a couple of days, 5 days at least, to have warmer than usual conditions. And this is an example of a marine heat wave of today for a month or so. And you see it's nothing really exciting because the heat wave is warmer than 2 sigma of the climatology, but it's still close to the freezing point, and we have a functioning Arctic ecosystem with phytoplankton, zooplankton, higher level consumers, fish, and so on. So that's a functioning ecosystem. What will happen in the year 2100? That's a marine Arctic heat wave in the future, in the most extreme one, I have to admit. You see again the lower one close to the freezing point, but in the year 2100, marine Arctic heat wave will start at 9 degrees or so in the Arctic Ocean and can go up to 13 degrees, which is enormous amplitude. And not only the warming is a problem for the biota, but also the strong cooling. So you can imagine that animals or biota have a problem to adapt to such an extreme heat wave in the future. That is a paper about what will be then the impact on the marine Arctic heat wave. We can also go in the deep past, that is 90 million years ago, so very deep in the past. That is, we published that in Nature 2021, and it also, we got this title page on this journal, and we engaged a painter. And this painter, we told him, based on our geological data and our model results, how the world looked like 90 million years ago, so-called Cretaceous. And this Cretaceous, people were lucky to find sediment data very close to the coast of Antarctica. And interestingly, they found roots, so fossil roots close to Antarctica, and these roots are specific trees, and these specific trees, they look like those trees which are drawn here. And from the existence of these roots and these trees, we can deduce the temperature close to Antarctica. And that is the result. So the triangle is where this was found, and the bubbles, they are a model result, namely temperature. The lower ones are here, South Pole, 280, 460, 1120. That's parts per million. So depending on the CO2 level in this Cretaceous climate, in our model simulation, we have a warmer climate or a colder climate. But here plays a big role that at that time there was no ice sheet on Antarctica, so the ice was absent, maybe a little ice, as in the picture below in the back, some high mountains, they have some glaciers. But that made the temperature on the planet, on Antarctica, very warm. That is our model simulation here in the middle. And you see that the warmest month temperature, which are the dashed lines, is difficult to see for you, but I tell you, depending on the carbon dioxide concentration in the atmosphere, the summer temperatures are going to 20 or even higher degrees in Antarctica in summer, and it is sufficient that trees can grow, although in wintertime it's almost dark. So this reconstruction data, this one data point or two data points here, close to Antarctica gives us a clue of temperatures at a greenhouse gas climate with very high CO2 level, and we can then in a model simulate the climate with different CO2 levels and then see which CO2 level is most consistent with the data. And that is around 1,120 parts per million, which is a lot, but this is interesting that if we have an absence of Antarctic ice sheet, we can get this. We cannot get these high temperatures if you if we have our present-day climate, that's the upper row, the bluish circles here, that is due to the ice albedo feedback. If we have a strong summer insolation in Antarctica, we have still ice, and if we have ice, we have strong reflectance, and then we never get above the freezing point. Basically, it's still pretty cold, at least here in the center. At the boundary, it might be warmer. So we have a kind of hysteresis behavior where we start. If we start with an ice-free, we get very warm temperatures up to 20 degrees. If we have an ice-covered planet there, we still have a cold climate. I will come to that, to the stability of the Antarctic ice sheet later in my talk. What has happened in the geological history? We start with the high CO2 level and almost absent ice sheets. And now we simulate in a truly coupled way ice sheets and climate. And that was published last year, 2024. Then again, depending on the CO2 level, if we decrease the CO2 level in the Earth history, so time goes from right to left, we are able to simulate then the inception of ice on Antarctica. And you see, if we enter into 1 times pre-industrial CO2 levels, 280 parts per million, we are almost entering into our present day climate. So this transition is very important. It's called Eocene-Oligocene transition. It's one of the biggest climate steps in Earth history, where we build up the ice and we're coming from a greenhouse to an icehouse climate. What we are doing now is going back in time somehow. We started from 280 and we are going back now to the right. As I said, we are already at 430 or so. Also, if you look not so distant past, so the last 30 to 20,000 years ago, we also had in the Northern Hemisphere a big ice sheet. And along with this big ice sheet evolution, we also have sea level changes. And they are quite dramatic. The sea level changes 120 meters below today. So we are missing water, and this water in the ocean was stored on land. So where was it stored? That is for 38,000 years ago. We had present-day Canada and Alaska, and big parts of Northern Europe were covered by ice. And these are different reconstructions or model simulations from 38,000 years ago. And the question is now, it's quite uncertain actually, but we did this in the middle, this is our reconstruction, but we said, okay, let's assume we don't know it exactly. We take a spread of uncertainties. And how does the Earth evolve if the ice sheet is evolving further? And what is happening is that the ice is growing. You see here 38 kiloyears before present to 21 kiloyears before present. We call that the last glacial maximum climate, where the ice sheet was in its maximum extent. And you see, independent on our starting point, the initial condition, we end up in a very similar ice sheet and also climate. This is, again, a coupled ice sheet climate simulation. And we have different trajectories towards that, but all the trajectories deliver lower sea level and a build-up of ice sheet. This is quite interesting. There is, again, climate feedbacks matter, and we can also calculate which are the dominant feedbacks in the system. So we can calculate in a model the snowfall and refreezing of water, and that is increasing a lot towards the last glacial maximum. We have also monthly melt is also it's going to be less, so reddish means here less, so we can, the latitude of the southern margin of the ice sheet is going to the south. So that is, this paper I think is quite interesting, that was published also last year with also a colleague who studied at OUC from Lou Niu, and this, I think it's quite a big step towards an understanding of buildup of ice towards the last glacial maximum. So this is, if you look in the last 140,000 years, this is somehow the forcing. We have two different kinds of forcings. I call it long wave radiation, the CO2 effect. If I translate the CO2 content in the atmosphere from the ice cores to the forcing in watts per square meter, you have about 2 watts per square meter lower than today, because the atmospheric concentration in CO2 was lower. So that's about 2, and in the future, depending on us, we will have, let's say, between 4 and 8 or 9 watts per square meter due to carbon dioxide. And this is a long wave radiation forcing. The short wave radiation forcing is due to the Earth orbital parameters you see on the right-hand side. The Earth is rotating around the sun, but this is changing, and then you can calculate the forcing. That's also in the order of 4 to 6 watts per square meter, cooling and warming phases in the climate system due to changes mainly here in obliquity, so the tilt. And that is what you observe, panel A, kind of fluctuations in the system, but they are modulated by this local summer insolation. Also a small cooling trend here in the last 10,000 years. But you see also these oscillations are quite dramatic in the system. So the past gives us somehow the view of what could have happened or what has happened in the past. We cannot exclude that such an oscillation will also occur in the future. These oscillations are dramatic. There's up to 10 degrees warming and cooling in the North Atlantic. You can make some time series analysis, as I did a couple of years ago. You can analyze at which time you have this transition. These are the reddish bars, and the blue things are here the points. And one can analyze then the waiting time between these events. And they can also number them with 1, 2, 3, and so on. And then these waiting times between these events are random. You can make an analysis. It's a Poisson distributed. So there's completely random. It can be a long time, can be very short time, and so on. So there are kind of stochasticity in the system where we cannot predict such an event. Interestingly, we can make more kind of little theory with climate change. We have internal variability, like weather, synoptic variations. So we have the weather is somehow also not predictable in internal variability. We have turbulence, mixing is also on this short time scales and relatively regional. One thing we cannot predict it. Then we have the seasonal cycle, which is nicely predictable. And then we have ice ages. There are also kind of periodicity behind it. And in between, we have, again, internal variability like ENSO or this Dansgaard-Oeschger-Heinrich events, which I showed just a minute ago. So we have in the climate system deterministic pacing, but internal variability, and that makes the life more interesting and more difficult, this internal variability. And now let's go back to our present climate. So what is the major challenge, or what is the dilemma that we face? The period of direct instrumental measurements is rather short. It's sparse. You see here ship routes, and we have almost no information about the temperatures in the Southern Ocean if you look for the period before the satellite area. So we need somehow information from the past, from past records, and from modeling to have an idea. And one result, also that's 2023, what we published here, is a stack of a northern and central Greenland ice cores. So basically the people collected ice cores for several years, and they measured it, and then we made a composite, basically averaging the signal, so to get a more regional picture of what has happened in Greenland. So the number of cores is it's about 20 or so. And what we see is we have again a lot of variations, a black curve here, and the thin gray curve is the original data. That's the smoothed one, the black curve. So let's see at the black curve, we have a small cooling trend in the last 1,000 years, and since 1800 or 1850, we have warming, and this warming accelerated in the last decade. And then we called it the global warming reached central Greenland. But to be honest, we don't understand completely this abrupt warming here in Greenland. That has something to do with atmospheric rivers. So we have an atmospheric situation where we bring very warm air to central and northern Greenland. And this, I analyze that now with a student, and this phases of abrupt warming events in the last 1,000 years is also random. So basically the waiting time between, for instance, this particular warming event and the next one is also random in time. But it seemed to be that here we have a cluster of, in the last years, decades, we have a clustering of more of these extreme events bringing warm air to Greenland. This is still work in progress. We can make also PDF, a probability density function, and then see, okay, how is the last or the previous decades compared to the distribution of the temperature, and it's clearly out of the range of the last 1,000 years. So this, for instance, is 2001 to 2020, 2011 average is quite it's quite above the outside the natural range of climate variability. I think it's quite interesting to get this data and to analyze it and compare to model runs. What are the model runs? What is our current state of model runs, at least in my view, which is subjective? And this is the ocean velocity, which we can simulate in climate models now. And you might have heard about CMIP, so a big model intercomparison project. This is a CMIP 5 phase, and you see here the Gulf Stream, but it's rather smooth, and this is somehow what most people are simulating if they are simulating the ocean. This is a special initiative, high-res MIP. Only a few groups can do that, and then you see already a quite more elaborated Gulf Stream, here also meandering, going to the north, bringing warm water to the North Atlantic. This is the frontier mesh. This is very high resolution. And here you see the satellite. If I wouldn't show you which is which, you cannot really distinguish that from observation. So this frontier mesh is now very nice, because you can have an idea of what is really happening in the ocean. And this is necessary. I wrote here, okay, we have a large uncertainty in regional changes, and we have also limitation of extreme events. And the example I showed you before was which with the paper was this marine heat wave. This is only possible with our most recent model runs, because only they have the right statistics. So only they have the marine heat waves, and they also have other advantages, because they also get rid of rule of thumb parameterizations. What is then a challenge in modeling? You need a scalable model. That means if you have more and more computer cores, so sharing the work on the big supercomputer, you need somehow a scalable computer system. That means a scalable model that you have also benefit of that. So you can really simulate a high resolution model with many cores. And if there's a line like that, you're very happy, because then you can simulate years per day. You can maybe simulate 60 or 80 years a day if you take more and more computational cores. So that means the challenge of today is that you have limited high performance computer capabilities. That's a challenge of today. But I say tomorrow, or what will be the challenge in the future, is more how to use, or how we are able to use our future systems, computer systems, in order to make the best simulation. So that is a computational aspect. And yeah, we want to get rid of this so-called parameterizations. They are not represented by the laws of physics, but are more rules of thumb. And as I said, we hope that we can reduce the large uncertainties in regional climate projections and extreme events. With higher resolution models, we have also new physics in terms of ocean circulation. And I guess it's okay. Here is an example of the so-called great salinity anomaly in the North Atlantic, where we have a very fresh, in the upper graph is salinity and here is depth. To the right is time, and we had a time in the late 60s, early 70s, where there was a big fresh event in the Labrador Sea, in this area. And at the same time, we have a big stratification, and the stratification led to temperature rise in the subsurface, whereas in the surface it was cold. Hopefully you see it. There were also times when it was different, like here in the 90s, where the temperatures are more homogeneous. So we have here more convection in the ocean, and then we have here temperature signals. So there is no cooling and warming dipole, but it's the whole water column can be mixed and can be warmed. And we can now distinguish between those phases where ocean convection occurs and phases where there is this kind of salinity freshening at the surface. That's quite important, because this is one source of climate variability. And that depends again on high and low resolution models. So if you have a low resolution version of the same model, that can make a complete different convection. Here's kilometers. So in this case, a low resolution version has a deep convection, but almost no time variation, whereas a high resolution version has a strong variation. And you can also analyze it with some theory. It has something to do with paraclinic instability and eddies, which are resolved in the Labrador Sea. Interestingly, also climate models have such kind of variability even on centennial and decadal, multi-decadal timescale, but they are not wanted. So you see also mixed layer depth. Again, here's 2 kilometers in this case. That was published also by an AVI colleague, but they tuned the model in order that this variability disappeared. Because the climate modeling people, sometimes they want to have a steady state and they don't want to have a variability. I think it's a mistake somehow, because the climate shows you also in the past strong sources of variability, and maybe such oscillating or fluctuating climate is more realistic than a steady state. But this is a matter of discussion. And here I have a question, okay, maybe we have to detune the models because such kind of variability is observed if you look in the paleo records. But yeah, it's a question if you want that or not. I guess I have too much material. I just want to mention, okay, where also is high resolution is necessary. AMOC changes. AMOC is large-scale overturning circulation in the Atlantic basin, and most models show a decline of AMOC in the future. Here's the year 2100. And if you compare the low and high resolution models, they are similar in a way. This decline, the structure is different. And what we found out here is also a paper, Physical Review Letters, just published last year. If you analyze the MOC, so the meridional overturning circulation, you get quite different results in the regional MOC. The Atlantic MOC is similar, but on regional scale, here the Greenland Scotland Ridge MOC is different in the high resolution model with 0.1 degree compared to a low resolution with 1 degree. It's even increasing the transport along the Greenland Scotland Ridge, and we are further working on that. What is the reason for that? It has something to do with convection in the Arctic Ocean, and then we have also different time behavior. So that is an example why we think high resolution is necessary in order to get the right response in the system. High resolution is also necessary in order to resolve specific processes, and this is a work which I did with Peng-Yang Song, a former PhD student, now postdoc. We implemented in our climate model the cavities. That means water below the ice shelves. This is typically not done. The ice shelves are swimming. They are fed by the inland ice, and the ice shelves are really resolved in our new model system. These are the reddish areas, and they're quite important. I'll show you just to give you a flavor of that. In the red and blue areas, so in those areas, they are most important. In the standard way of models, depending on the climate scenarios, we have some more water entering into the ocean. However, if we are including those ice shelves, they're quite vulnerable, and we get quite different gigatons per year in order from fresh water if we have allow for this basal melt at the ice shelf. This is just to give you a flavor. Okay, we need some model development also to pick up weak parts of the system, and they are kind of tipping points in future climate and also in the past. Okay, just to summarize, and emerging pattern of initial stage of warming. It seemed to be a model shock, variability, the resolution matters. We have also regional signature of tipping. We have feedbacks with the cryosphere. Finally, okay, why I think climate science is so exciting. Modelers, but also people going to the field, they are collaborating. I think it's a big international organization and people who are really working together. That's somehow unique. We work on the same subject across disciplines, but also across cultures and countries. I think you as more younger scientists should take the opportunity to get into exchange with others, work together. For me, it's also cultural exchange with other culture. It's a big opportunity in life. And also somehow what is also nice to work as climate scientists, we somehow want to save our future and understand what is happening in the past and in the future using all these interesting methodologies. Yeah, thank you very much for your attention, and I'm interested on your questions.
Yeah, thanks a lot. Any questions? You can just switch on your microphone or just draw something in the chat.
Hey Gerrit, thanks for your brilliant talk. And in one slide, you show that in the past there is thousands of meters thick ice shelf in the North America. And I'm very interested in that. Do you have any idea on the ice thickness in the Arctic at that time?
So the ice thickness is up to 3 or 4 kilometers. Yeah. In the ocean, it's a big discussion. I'm also working on that because sea ice is very important. It's a big isolator between the ocean and the atmosphere. And if you have a very cold climate, like here in the last glacial maximum, then we have strong winds and strong heat flux. And this heat flux, this heat loss from the ocean, leads to a strong build-up of ice. And in the last glacial maximum and in the other glacial maxima, it's a big discussion if the Arctic Ocean had a sea ice of a couple of meters sea ice thickness, maybe 10 meters, but others claim this has 1,000 meters. It's a big discussion. There was, I think I have a slide for it, but I dropped it. There's a big discussion about that. No, I doubt it. How thick is the ice in the Arctic Ocean in ice ages? And that has big implications. And I think there are good reasons that it's not too thick, but others are claiming it's a 1 kilometer thick ice shelf in the Arctic in glacial times.
Thank you. So it seems that the ice thickness is still unknown at that time, right?
I think there are good indications that it's not completely covered. There are some indications that it's still moving. So geological evidence shows that you find material, basically stones, in the Fram Strait and in where it originated from present-day Canada. So there must be some movement within the Arctic Ocean. There's also another reason why it's interesting. I think there's also the high resolution models. They show that you always have ice-free regions in the Nordic Sea, but also in the Fram Strait, in the last glacial maximum. That has something to do with katabatic winds coming from the glaciers. But this is also, we just submitted a paper to Science about that. So I think it's also a big discussion and which kind of physical process is behind this open water in the past. It's also a good test playground for climate models if they're able to show that.
Thank you.
I found another question, but in the chat. I just read it for you. So, thanks for your nice talk. I would like to know, under the warming climate and decreased sea ice formation, the deep ocean circulation triggered by the sea ice brains would become stronger or weaker, like the ABW. Some found strong ABW. Sorry, I don't work on the paleoclimate, and maybe you can just answer this.
Some strong Antarctic bottom water in the Miocene and PMOC in Pliocene, but not in modern observation. That's true. That's an interesting statement. I don't know who wrote that. Dong from FIO. Okay, I think it's interesting. Indeed, the Antarctic bottom water is also quite interesting because nowadays it's built partly in ocean waters, but mainly in the ice cavities. In warmer climates, it's probably only open ocean convection. I need to discuss it with this person. It's an interesting idea. The PMOC, also Pacific meridional overturning circulation in the Pliocene. Okay, I'm interested in that. He or she should contact me.
But honestly, I don't think currently climate model can really simulate such kind of process. As far as I know, for such kind of brain rejection, during the ice formation, there's typically quite some different parameterizations that could bring totally different results.
Yeah,
I think this is a very, very, very good topic and very interesting. Yeah. Everyone knows this, but the problem is that as Gerrit said, that if you have very high resolution, climate models, maybe you can do this. Yeah.
But I think it's quite complex with this brine formation. For instance, in the last glacial maximum, the Antarctic bottom water was very salty, whereas today Antarctic bottom water is very fresh, and that's somehow astonishing. But the reason is that the brine formation, if you produce sea ice, if you have a fabric of sea ice production, and then the sea ice export towards the equator, you have a strong sea ice production, which leads to this very salty bottom water in the glacial times, unlike today where it's fresh. So I think we need to understand this process for warm and cold climates, and I think it's a very important question because it also has something to do with CO2 storage in the deep ocean. Yeah, but it's complicated. In the models, it's not easy.
Yeah. So, any questions?
Maybe I touched too many topics, but I tried to give you an overview and what is, at least in my view, challenging aspect of climate change.
Yeah. So Gerrit, just another question is a very simple question maybe for you. So for the paleoclimate or the past climate, at least we have some observations to validate our model results.
Yeah.
But for currently, you see that so many researchers that talks about the future but without any validation.
Yes.
Does that really make sense?
Yeah, I think we need both, but one argument or one strong argument for paleoclimate is indeed that gives an independent test of our climate models, and we get more trust in the future if we understand the past.
Mm-hmm.
And, this statement I tried in the last 20 years to show, okay, if we have newer models available, you should test them into the past, starting last 50 years, but also they should be able to be good in the last 1,000 years, and then 10,000, 100,000 years. And it's a very good test case for models. Also, one can ask also why we need this ice sheet evolution, the buildup of ice sheet, but we need somehow to understand the coupled system with interactive ice sheets in climate models, and then we need to understand what process is relevant for melting and buildup of ice sheets. I think without the paleoclimate, we cannot deal with ice sheets.
Yeah,
this is clear. But of course, other people are more interested in impacts of the next 10 years or so. But I would say that it is also interesting by itself, extreme events. I think it's also necessary to do research on that. But then I would also ask, what is then the long-term context of these extreme events, either in the ocean or the atmosphere, on long time scales? Is it more extreme events happening in warmer climates or less? And where? And again, I would say the long-term perspective helps in this respect.
Mm-hmm. Yeah. So we still have some. Oh, we have 2 minutes. Maybe one more question. Mm-hmm.
You can ask any question. Don't be shy.
Mm-hmm.
Yeah. Maybe I spoke a little bit fast, but you can also contact me or then
okay.
Particular questions.
Maybe tomorrow is Saturday.
No problem.
Okay. So I just wrap up. So thanks again for your very nice talk, Gerrit. Thanks a lot. And maybe we can. I can see you. In the Army this year.
Yes, it would be nice. Yeah.
I wish you all. Plan.
Yeah, I wish you all the best for this year.
Okay.
Hopefully, it's a year where people can advance in their personal careers, and also that it's peaceful for all of us. I wish you all.
Thanks a lot.
Yeah.
Thanks a lot. The same to you. Yeah, the same to you. Okay, so wish you have a nice weekend and a nice year. Okay, so let's see for the students, if you have any questions, please just drop emails to Gerrit Lohmann. Yes.
Yeah.
Okay. Thanks a lot, Gerrit.
Yeah. See you.
Yeah.
Bye.
Bye.